Here we have an extremely common problem with an energy. We have a ball sitting on top of a hill, which it will then roll down. It starts from rest, but it starts to roll down this hill. It'll have a certain velocity at the bottom of that hill, and then it'll climb a second hill that's not as tall as the first, and it'll have a different velocity. Then it'll reach the bottom of that second hill, having the same velocity as we find right here, and then it will reach this point where it will have a friction that will slow it down. Everything until this point right here is a closed system. The mechanical energy, the total mechanical energy for all three of these points will be exactly the same. So let's give this a mechanical energy. Say it's ME equals, let's just say J, number of joules J. Well, at this point, it will also be equal to J, the total mechanical energy. All of it will be equal to that amount. Now, at each of these points, we could have either potential or kinetic or a mixture of both. So let's say at each of these points, J is equal to however much kinetic energy I have plus however much potential energy I have. This is where students begin to struggle when we talk about energy, is they have a hard time wrapping their heads around this total value, this value of J, which let's just say for argument it's 500. This total value of J stays the same at each of these points. All three of these points, the value of J will be exactly the same. The only thing that's changing is how much of that energy is being put in the potential energy pile and how much is in the kinetic energy pile. So in our first moment here, all of that energy will be in the potential energy pile. Why? Because my velocity is 0. I begin from rest. And so we're going to say our total mechanical energy will be equal to, we've got our equation for kinetic energy, that's 1/2 mv squared. And then we have our potential energy, and that equation is mgh. So we are, at all three of these points, we're going to use this exact same equation. The only thing changing in any of these moments is the value of v and the value of h. So let's get started. Let's give each of these variables a number. This will be h1, v1, h2, v2, h3, v3. Since ME, my total mechanical energy, is the same at all 3 points, I can say that the kinetic energy plus the potential energy at point 1 will equal the kinetic energy plus the potential energy at point 2. So we can write that this way. K plus U K1 plus U1 will equal K2 plus U2. Now, let's write out our actual equations here, and we'll see how this simplifies right off the bat. So if we look at this, what we're really saying is the mechanical energy at 1 versus mechanical energy at 2. We're comparing these 2 points here. What is my kinetic energy at point 1? Well, since my velocity at point 1, my velocity is 0, my total kinetic energy would just be 0 squared, which is 0, times m, which is 0, times 1/2, which is 0. So this whole term becomes 0. And then at point 2, what's my height? My height is 0. And so 0 times 9.8 is 0. Times m is 0. So this term cancels out as well. And all I'm left with is the potential energy at point 1 will equal my kinetic energy at point 2. And so one other point can be made here. These masses are for the same object. So those masses are equal. So as long as we are staying inside that system, as long as we don't have to figure out how much work is done on that object, we don't need to know its mass. We can divide by m and we'll be left with a simpler problem. So now that we have this simplified problem, we can solve for the velocity at point 2. Let's plug in some numbers. We're going to have a 9.8 for our g times our initial height of 20 equals 1/2 times v squared. First thing I'm going to do is multiply both sides by 2 to get rid of this 1/2. Then I can square root to get rid of my square. And so the square root of 2 times 9.8 times 20 will equal my velocity. And when I make that calculation, I get a velocity of 19.8 meters per second for V2. So my velocity at the base of this hill is 19.8 meters per second. Now I can do the exact same thing with this third section. I don't even need to use different numbers. I don't need to reset up this problem. I can just say this same value, since I already know all of my mechanical energy at point 1 is locked away in that potential energy, I can say that mgh1 will be equal to mgh2 plus 1/2 mv2 squared. Or I'm sorry, these should be 3. All right, now if I look at my variables here, I do have a height. I have a height for my potential energy in height 3. So I am going to have a value here. I still have the same mass in all 3 terms, so I can knock that right out. And I end up with 9.8 times this height, which was 20, that's my first height, equals 9.8 times my third height, which is 5, plus 1/2 v3 squared. Now I can simplify these. And when I do this, what I'm really saying is, of that mechanical energy, 49 will be locked away in potential energy, and the rest will be in my kinetic energy. So if I want to figure out how much kinetic energy do I have, well, I just need to subtract 49 from that. It's like saying, well, I have a total of $10,000. Some's in checking, some is in savings. And you go, well, how much is in checking? You can go, well, I've got 8,000 in savings. Subtract that, and now you know how much is in your checking account. So let's take that, 196 minus 49. And we're going to have 147 equals 1/2 v3 squared. Now, we can take that 1/2, multiply both sides by 2, and then take the square root of that, knocking that out, knocking that out. We end up with 17.1 for our V3. So there we have been able to figure out our velocities at each point on this set of hills. But now we have one more part. We have a point of friction where we will have our ball doing work on the ground, effectively heating it up. Think of a car when it stops. It uses brake pads, applying friction to a brake rotor. What happens to that brake rotor as it stops? Well, it heats up. It heats up a lot. Those things will get extremely hot. All of that energy, all of the kinetic energy of the car is being dumped into heat energy at that brake rotor. And so that's really what friction is. We call this thermal energy. We consider this the work done by friction, and we consider it a waste. So this is wasted energy. Oftentimes in engineering, we have to think of ways to get around friction because if we're trying to spin a turbine to generate electricity, every bit of energy that has to go into thermal energy to combat the friction in a rotor, that's energy that isn't being converted into electricity. That is lost energy. It's a wasted energy. So it is important to be able to consider that. But what's really happening here is we're having the work of friction. So we have work being done by the force of friction times a distance. Well, how do we calculate friction? Well, that's going to be Fn times mu k, which is then still times d. Well, what's Fn going to be? Well, Fn is just going to be the opposite of our force of gravity. And since these are all scalars, we don't need to worry about positives and negatives. So our force of gravity would just be mg, then times that mu k, then times that d. So whenever we're looking at the force of friction, the work done by the force of friction, we can say mg mu k d. And so we can set this amount equal to our initial potential energy. It's going to be the same amount. If we have no height left and we move until we get to a velocity, let's say a velocity of 0, so v4 equals 0, then all we have left is a distance to do work on. And so let's set that up. We're going to use just that same initial condition, just like we've been using before. So our mgh1 will be equal to the work done by friction, which will be mg mu k d. Now our m's still cancel out. Those can still be divided out of each term. And we end up with gh1 equals g mu k d. Now we have g on both sides, so we could actually factor that out as well. And what we end up with is our initial height of 20 will be equal to our mu k times d, which was 0.5 d. So we can divide both sides by 0.5. And so I will end up with 40 for final distance. So this object will be able to travel a distance of 40 meters before coming to a stop based on that coefficient of friction. So we can see here that throughout each of these steps, because my total mechanical energy was the same for each step, I was able to say, hey, let's just figure out my initial value here, my initial amount of energy, and then use that value to figure everything else out. It's the same each time. So in 4 distinct situations, 1, 2, 3, and 4, my total energy was always the same. It remained unchanged.